This is Ref, Brown University physics grad student. Today I'm going to derive the conservation of energy for a black hole. So let's get started with the Schwarzschild metric for a black hole. To describe everything about a black hole, you need only one equation. This is called the Schwarzschild equation. You see, Carl Schwarzschild, just 6 months after Einstein published his field equations, Carl Schwarzschild found the first solution to the field equations, and that first solution was none other than a black hole. And this is what his solution looked like. Carl Schwarzschild wrote down this equation: ds squared. ds is a small step in space-time around the black hole. In fact, you know what? Let's write it with red, because this is probably the most important equation you'll see in the whole video. ds squared, a small step in space-time around the black hole, has some time component plus some space component. That's it. That's all there is to a black hole. To understand a black hole, you need to understand this equation. Okay? Now let's break it down. First of all, a real black hole is a sphere. It's not a flat object. It's not a box. It's not a plane. It's a sphere. And to describe a sphere, you need to use spherical coordinates. So you cannot use x, y, z, or you can use x, y, z, but it's very complicated to describe a sphere using x, y, z. Instead, you should use spherical coordinates, r, theta, phi. So the sphere has some kind of a radius. That's your radial coordinate. And then you can describe two kinds of angles around the sphere. An angle on the plane of the sphere, this is the phi angle, and an angle that's about the plane of the sphere, that's the theta angle. So those are the coordinates used to describe a sphere, spherical coordinates. So instead of writing dx here, I'm going to use spherical coordinates, which is dr squared, and then some coefficient around the d theta squared term, and then similarly some coefficient around the d phi squared term. Okay, very good. Now, what are these coefficients? Well, first of all, for the theta and phi squared coefficients, they look exactly like the coefficients for a regular flat plane. So for theta, this is the coefficient, r squared d theta squared. And for phi, the coefficient is r squared sine squared theta d phi squared. Very simple, very simple. But for dt and dr, that's where the black hole comes in. That's where the black hole makes an appearance. For dt, we have 1 minus 2m over r. And for dr, we have 1 minus 2m over r to the minus 1 power. So now if I write all of this down as just one equation, the Schwarzschild metric, then it looks as follows. Let's erase all of this. And let's write down the single equation describing a black hole. This is the Schwarzschild metric. And this is going to be what we play around with today. So minus 1 minus 2m over r dt squared plus 1 minus 2m over r to the negative 1 dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Okay, this is the equation for a black hole. Now, this equation tells us how time, how radial coordinates, how angular coordinates change around a black hole. So it tells us how time changes and how spatial coordinates change around a black hole. So today what I'm going to do is derive the conservation of energy for a particle orbiting a black hole. So what do I mean by that? By conservation of energy, here's what I mean. Conservation of energy says that the total energy for any object is the kinetic energy. Let's use K for kinetic energy. The total energy of any object is the kinetic energy plus potential energy. Now, for a particle orbiting a black hole, this equation has a very specific kinetic energy and a very specific potential energy. And I'm going to show you what these kinetic and potential energies are now. Okay, so let's go ahead and take a look. First of all, what do we want to do? I want to write down what the total momentum of a particle is when it's orbiting the black hole. Here's a black hole. The black hole has some Schwarzschild radius, R sub s, which is 2gm over c squared. M is the mass of the black hole. G is Newton's gravitational constant. C is the speed of light. And here is a particle that is orbiting the black hole. Here's a particle orbiting the black hole. Now, this particle, let's say it has some mass, lowercase m. To describe this particle, I'm going to need a velocity vector. So here is a velocity vector for my particle. And in general relativity, velocity is actually a 4 vector. It has 4 components, a temporal component and 3 spatial components. Now, this can be broken down as dx mu d tau, which we can further break down into dx mu dt, dt, d tau. Now, dt d tau, if you remember your special relativity, is just gamma. And so this is gamma times dx mu dt. And so the velocity 4 vector is actually simply gamma 1 comma v, where v is its velocity 3 vector. Now we can write down the momentum 4 vector for the particle as the mass of the particle times its velocity 4 vector. So this would be m gamma 1 v. Okay, so this is the momentum 4 vector of our particle. And more generally, the momentum 4 vector has this temporal component and those 3 spatial components. The temporal component of the momentum 4 vector is actually just the energy of the particle. And so now we can write that the p mu is equal to minus m squared. What does that mean? Well, this is just another way to write E equals mc squared. How so? Well, let's go ahead and expand this out. This is going to be minus p0 plus px. Remember, in special relativity or general relativity, the dot product of 2 vectors comes with a minus sign for the first temporal component because time has a negative sign in the Minkowski metric, which is negative 1, 1, 1, 1. So this is where that minus comes from. And that's why all the spatial components have a plus. So pc, pz, this is equal to minus m squared. Now all of this is simply the magnitude of the momentum vector squared. And this is simply the energy squared minus the energy squared. This is equal to minus m squared. Now if I solve for E, I simply get E squared is equal to, let's bring back the, okay, maybe I'll wait a little bit. This is what we have. Now if I solve for the energy, I get this equation, which might not look familiar until we bring back the speed of light into this equation, which says that E, the energy of our particle, is the momentum times the speed of light squared plus mc squared whole squared. Now that means if our particle is at rest, then this P is 0. And so that means the rest energy of our particle is simply the square root of mc squared whole squared. And now if I just simplify that, this is our famous equation from Einstein, E is equal to mc squared. One of the most powerful equations of the 21st and 20th century. So now we're going to use E equals mc squared to calculate the conservation of energy for a particle around a black hole, starting from this equation. So this equation is no more than E equals mc squared disguised in another form. But now we can use this equation to derive the trajectory of a particle as it orbits a black hole. So let's erase all of this. I'm going to expand this as follows. So P mu, this uppercase P mu with a contravariant upper index, we can write it as G, let's see, do I want to write it as, yes, let's write it like this, as G Okay, let's write it as G mu mu P mu P mu is equal to minus m squared. So what I just did is I so-called lowered the index. So this G to the mu mu times P sub mu is equivalent to P to the mu. Essentially, multiplying these two contravariant indices with this covariant index raises the index like this. Or if you follow the operation backwards, it lowers this upper index into a covariant index. So that being said, why did I do that? I did that so that I could introduce the metric, G mu nu, this metric where the black hole is hiding. I wanted to introduce that into the equation, and now I have done that. So now, if I just go ahead and simplify this a bit, this is P sub mu squared is equal to minus m squared. Now, G to the mu mu, that is where the black hole is hiding. So we're going to expand this as GTT, the temporal component of the metric, times P0 squared, plus GRR, P sub r squared, G theta theta, P sub theta squared, plus G phi, P sub phi squared is minus m squared. Now let's write down the Schwarzschild metric in matrix form. That's going to help us simplify this expression further. So let's erase all of this, write this down in matrix form. So in matrix form, the Schwarzschild metric looks like this. G mu nu. Now, first let's write it as its regular form. So I have minus 1 minus 2m over r for the time component, 1 minus 2m over r for the radial component. Now, if we assume our particle is orbiting around the equator of the black hole, then theta is a fixed parameter, simply pi over 2 for a particle orbiting around the equatorial plane of the black hole. And so d theta is actually just 0. So simply there is no d theta component. And by extension, there is no p theta component in the expansion of p mu mu. Because remember, p theta is no more than u theta divided by m. But this is simply, if you can see this far, this is simply d theta d tau divided by m. But if theta is fixed as pi over 2, then p theta is simply 0. And so this term in the p mu expansion goes to hell. What about the other components? Well, this is r squared, and r squared times sine squared of pi over 2 is just, once again, r squared. So I have r squared for both of these here. So now what I'm going to do is I'm going to invert the metric. So we're going to raise both of these indices because we have the inverse metric over here. Now if I do that, this takes on a -1. Here this reciprocal dies. This is r to the -2, r to the -2. So now I can begin just plugging in. This GTT here, that's simply going to be this term, the temporal term for the metric. -1 minus 2m over r to the -1. P0 squared, P0 squared, plus, let's see, GRR is 1 minus 2m over r. We have P sub r squared, plus G phi is r to the -2, P sub phi squared. And that's equal to minus m squared. Now, what can we do here? Let's see. So we have 1 minus 2m over r. Okay. So let's see if we can make some simplifying assumptions here. So p phi, what is p phi? Let's write down what these momentum coordinates are. Maybe that'll help us simplify things. First of all, we know that the energy of the particle, let's erase the metric here. We already used it up. Its utility is served. So let's write down all the components of the momentum 4 vector for our particle in spherical coordinates. So first of all, let's consider the P0 component. This P0 component, where does that come in? Well, we can write the effective energy of our particle, E tilde, as P0. Should I do it up, lowered or raised? Well, I'm not sure. I think let's do it lowered. Let's lower all of these components here. So this is P0, PR, P theta, P phi. So this is P sub mu. So this is P sub 0 divided by m, the effective energy of our particle. What about P sub r? Well, P sub r is the radial component, and that will be changing. So let's see, I can write P sub r as maybe just dr d tau. What about P sub theta? Well, for a particle that's orbiting in the equatorial plane, theta is going to be fixed as pi over 2. So, in fact, let me just write it. P sub theta would be d theta d tau. And if theta is fixed, this is just 0. And finally, P sub phi, what's that going to be? Well, that's going to be related to the effective angular momentum of my particle, which is simply the P sub phi component divided by m. Great. So that means if I now solve for my P sub phi component, P sub 0 component here, that's just m times the effective energy. And likewise, this P sub phi component is m times the effective angular momentum. So now I can start plugging these things in here. So P sub 0 squared is going to be m times the effective energy squared. P sub r squared will be dr d tau squared. And P sub phi squared is going to be mj tilde squared. Mj tilde squared. Now let's just go ahead and expand this out. So we'll have minus 1 minus 2m over r to the minus 1 plus 1 minus 2m over r, that's fine, and plus r to the minus 2. All of this is equal to minus m squared. So let's see if there's any simplifications I can make. So first of all, this I forgot, there should be an m here because this is momentum is m times the forward velocity. So this should be times m. So immediately one thing we notice is that the mass of the particle actually cancels out. So here's my mass, gone, 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 gone. Okay, so now we can hopefully bring this up over here and simplify this further. So we're well on our way to obtaining the conservation of energy for this particle. Okay. Let's erase all this. All right, so let's write this down. So I have, actually, we don't need the momentum 4 vector components either. So we don't need these. So let's just write this down. I have minus 1 minus 2m over r to the negative 1 times the effective energy E tilde squared plus 1 minus 2m over r times dr d tau squared. That's like a kinetic energy term. And finally, j tilde squared over r squared. And this is all equal to minus 1. Okay, now let's solve for kinetic energy dr d tau squared. Let's multiply through by 1 minus 2m over r. So if I multiply both sides, or actually, yeah, let's multiply both sides by 1 minus 2m over r. So then I would get minus e tilde squared plus 1 minus 2m over r squared dr d tau squared plus j tilde squared over r squared 1 minus 2m over r is equal to minus 1 minus 2m over r. Wow, that makes it horrible. But, wow, that's nasty. Oh, God, that's bad. Okay, let's not do that then. let's not do that. Let's just solve for this kinetic energy dr d tau term first. Okay, where is that? So I'm going to bring this left term over to the right side and the angular momentum term to the right side. So I have 1 minus 2m over r dr d tau squared is equal to we have E tilde squared times 1 minus 2m over r to the minus 1. Okay, that should be fine. And then we have minus 1 minus j tilde squared over r squared. Okay, now if I divide by 1 minus 2m over r on both sides, I get dr d tau squared is equal to E tilde squared times 1 minus 2m over r to the minus 2, and then minus 1 plus j tilde squared over r squared times 1 minus 2m over r to the minus 1. Okay, so I may have made an error in some part of the derivation because we're almost there, but if you simplify this further, the final result will be dr d tau squared is equal to E tilde squared minus 1 plus j tilde squared over r squared times 1 minus 2m over r without a reciprocal. So go back, watch the video again. If you can find my mistake in deriving this last part, then congratulations, you're an expert in GR. But this is the essential method for, this is the basic idea for deriving the conservation of energy for a particle orbiting a black hole. Thanks for watching. We'll see you in the